Okay. So yesterday we talked about force and force convection. So again, I just want to maybe after you watch the videos or the recordings and then check again for some reason. So this is a typical question or problems for force convection. For example, you can be in the inside the fluid, inside the pipe, there is a fluid that is flowing with some velocity. It is usually a close, a close pipe, or that means that all the fluids filling the pipe. So it is like a closed system, okay, with some velocity, and then when it is traveling along this length z over here, that is uh, co- uh, uh, constant, yeah, the heat flux. So it can be heated up or it can be cooled down, maybe with some cooling water, or I think maybe with cooling water. Some example would be the double pipe heat exchanger, okay. Okay, and then we also think that first from the momentum balance, so this is a combination between the momentum balance can be combined with the heat transfer, yeah. So from the momentum balance, we know that the velocity. Sorry, I think I need a glass of water first. Okay, so from momentum balance, you have profile, this one, yeah, which is a VZ, but sometimes in some other case, we just say that the velocity is the average velocity, yeah, so velocity average. Okay, and then after that, we do again the energy balance. Okay, so if we'll consider this is as a cylinder with cylindrical coordinate, and then you see that in the z direction, which is with this axial, we know that that would be a conduction, yeah. Why? Because there would be a difference in temperature in here. Okay, so if you think that there is any difference in temperature, then that you should think about conduction. Okay, and the second one, because there is a flowing fluid, okay, and then with some difference of temperature, then you need to consider convection, okay, there. And then on the over there, with the r direction, there is no velocity to the r direction, but there would be some temperature difference with the conduction. Why there's temperature difference? Because around here from the outside there's a heat flux. Okay, see if you can see here, on the outside here there is a heat flux, so there is a heat that is transferred outside. So of course with the r direction would be a difference in temperature. Okay, so because of that, then we can find some ring or a shell like this, and the shell is actually would be a function of we can cut it with the dr, and also we cut it with dt. Okay, and after that we can check the thermal energy in and thermal energy out with this one, yeah. So I think this is similar with the circular pipe case. So you have to just think all the area that is cross section with the Q. Okay, you see, check the arrow of the Q, and then you get the area. Okay, so this is the area that is perpendicular to the QR, ya, luas yang tegak lurus dengan arah QR. Okay, so if you go back here, the QR is in that direction, so the area would be that one, yeah. Okay, or 2VR multiply with delta Z. Okay, or on the outer one would be 2 VR for the outer one, multiply with delta Z. Okay, and if you consider about the area that cross section, which is perpendicular to the Z direction, that would be 2 VR, and then multiply with the delta R. Okay, so it looks like a thin rectangular, yeah. So here this is 2 VR delta Z, and to the Z is 2 VR delta R. Okay, and then when you look at here and then divide it with 2 feet delta R delta Z, then you get it something like this. And after that, maybe you need to try it by yourself to find, and then again for the convection. Okay, so for the convection, it is written as, I think you need to write it out. So this would be rho Cp Vz, the delta Z at Z, and then the outside one would be rho Cp Vz, the delta T at Z plus delta Z. Okay, and then we multiply with the area that is perpendicular to the direction of the convection. Okay, so in the end you end up with this form, and then you can put the limit to delta R close to 0 or to delta Z close to 0, and after that you end up with this partial differential equation. Okay, and then so that would be the QR, and also that would be QZ. So this one is the equation for heat flux. Okay, if you want to know the distribution of heat flux, for example, that would be this would be the equation of heat flux. But the thing is, we don't know what is QZ and what is QR. So what the next thing we need to do is to substitute the Fourier's law with the QZ and also the QR with this equation. Okay, so here we can get that this would be the equations, and then then the conduction to the Z direction is very small compared to the convection to the Z direction. Okay, so this conduction to the zero direction often is ignored. It can be neglected. So then you can get this partial differential equation where the temperature would be a function of T, the function of radius, and also the function of distance. Right? Okay, and then this is the boundary condition. The boundary condition is when R equal to 0, or when on the center or of the pipeline, or the center of the tube, or on the axle, we have a temperature. The temperature is finite. So then that means that your T would be finite. Okay, so or the T is not equal to infinity. This is very important because sometimes when we derive it, usually the R would be on the denominator, ya, akan ada di penyebut, ya. So when R would be in the denominator, then it is very important for us to say that the T would be finite. Okay, the second boundary condition, we know that I can go back over here. So if you look at the boundary condition based on the phenomena here, when Z equal to 0, the T would be equal to T0. Okay, that would be the reference temperature. And the second one, when R equal to capital R, which is on the wall, there would be a heat flux with the Q equal to maybe with the Q equal to Q1. Okay, so that one maybe with the T1 something. Okay, so here would be like this one. Okay, so this is the boundary condition, or then on the second one would be Q1, and would be z equal to 0 equal t equal to 0. And then when you finish, I think because this is a function of a dou z and also dou r, when we solve it, we can't maybe do that analytically, but we can solve it with numerically. Let me check for a handout. I think I have a handout from Pak Anggit, yeah, few years ago, that he considered about some equation. Okay, I think this one would be okay. So let me just stop share this, and then okay. So this is from Pak Anggit a few years ago. Okay. So yeah, this is similar. Yeah, this is similar that what I explained it, and from here. That would be this one, yeah. So this is the one that is actually quite similar. R equal to 0, t equal to finite, r equal to r, k equal to dou t over dou r, q0, and then also t to t1. Okay, and then so this is the boundary condition. This can't be solved analytically like with the integration, because this is a function of dou z, and also this one is a function of dou r. So what he did is actually we can use the partial differential equation, which can be solved with numerically, yeah, using finite difference method, using MATLAB, FlexPDE over Excel, or even Excel. And then this would be explained later. Yeah, so Pak Anggit also will give a lecture about how to check this one. So for example, this is the heat flow in a pipeline. In this case, that if you look at here, I think around this one here, this is going to be the wall. So we actually like slice them. Okay, so we slice them with only with r, a function of r and z, and then so the function of theta is we slice them like that. Okay, and then in this would be the wall. Okay, so this would be below. So try to imagine that this one would be the wall. So maybe I can draw over here. Yeah? Okay, so let's try that this would be the r equal to 0. This would be the wall, r equal to r. Okay, so this would be r equal to r on the wall. This one also r equal to r on the wall. And then this one would be when z equal to 0. Okay, so when you if you look at here that the fluid over here is equal to T0, maybe around the maximum, maybe about 200 something, I don't know, yeah, 200 Fahrenheit maybe, or something. Okay, the temperature. And after that, because you have a Q1 over here, so that would be the heat is transferred outside, so that would be a cool over here. So if you look at here, that on the wall is actually quite cooled down. Okay, and then you can see that the temperature around here would be a function of r and also a function of the z. Okay, so you can usually in FlexPDE or in computational fluid dynamics, we can see the difference of the color. If the high temperature usually become red something, yeah, it's like the black or the red one. And then after that, so how we read the color or how we read the temperature, usually we look at by the color. So for example, what is the distance, the temperature at this distance on the center point? So this would be like light blue, so maybe around 90 points, for example. Okay, so that is our finished dimension. The second one here, in here, okay, up to here, and then this one, we can see what happened if we try to draw with a three dimension. Okay, so in this three dimension here, we have three coordinates. On that side is the x, or in this case would be the z direction. So this is would be when z equal to 0. Okay, on the middle, to that side and that side is all would be the r direction. Okay, so this would be the middle. Okay, so and then we add one more, is actually the coordinate for temperature. Okay, so that would be the temperature, the maximum, and then after that it will start cool down on the wall on that side and also in that side. So the temperature will be cooled down this way, and then after some distance, then the temperature would be similar with the outside temperature, or because of the Q, yeah, or that one. Okay, so that is the partial differential. Of course, it would not be included in the exam, but again, Pak Anggit will explain to you more about the software, so at least you know how to use it, and then later on, if you maybe if for example for next project, or for final project, or for example if you have to change it with simulation. So this is an example of simulation, how to simulate using the principle of a transfer phenomenon. Okay, so again, so I'm gonna go back to here. So this is also quite similar here. This is like I will also give this one for you, but this one is actually using the approach from the book, while the one that I explained to you is the approach from the handout with Pak Danu for over the years. Okay, so you can see. I think the one that I explained to you before is more simplified. We just consider the convection and conduction, but in here we consider all of them. Yeah, the Q is changed into E, the energy over here. Right. So and then one more, when we do the differential equation over here, so sometimes it's easier for us to convert it into a dimensionless form. Okay, so in the dimensionless form, like Pak Anggit explained a few weeks ago, the dimensionless form is actually a quantity when we divide our variable with some number. Okay, so for example here we have what is this, zeta, epsilon or zeta, yeah, this number here would be equal to r divided by capital R. Okay, or maybe I think I need to just continue with the handout. The handout should have. Oh yeah, okay. I think I'll just stop share here, and then I'm gonna go back with the handout, because the handout also have that one. Okay, so here, we will start with the persamaan tak berdimensi, yeah, or dimensionless equation. Here we have temperature. We know that it is a function of radius and r, and then this one is a function. So the temperature is changed into theta, and then r is function. I forgot what is the name. Wait, let me take the Greek alphabet so I can say it right. or C, yeah. So this one is C xi, this one is function of C, and this one is function of zeta. Uh, so 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 we change T with the temperature with theta, yeah, with the function of theta, and also the R with C. It's called XE, yeah, or C. So let me write here. Can I write? Okay, so this would be wait, go back. Do I share my my PDF? Hello?
Yes, Bu.
Oh,
Yes,
yes.
ma'am.
Yeah, okay. Wait. Okay, so this one is C. Okay, and then this one is Earth. Or it would be Zeta. Okay, just want to say. Okay, so this one C. C would be the dimensionless form of radius. Okay, so it would be R equal to R divided by capital R. So that means at R equal to 0, so the C become what? R equal to 0, C become 0 divided by R, which is 0. So you change them, the variable from R into C, or this one, yeah. Okay. So when R equal to capital R, so the C would be R divided by R equal to 1. Okay, so then so if the C is between 0 and R, then it would be between 0 and 1. Okay, would be a fraction. The second one would be the theta. Okay, we know that the difference, the quantity for temperature, usually using the temperature difference with the reference using T0. Okay, and then it is divided by the dimensionless, or the with the similar unit, harus sama unitnya. Okay, satuannya. Okay, so this one with the Q1 R over K. So this one, the unit is temperature, for example Kelvin, and this also temperature, for example Kelvin. Okay, so that would be similar. Okay, with this one again, we also can see that when the theta, so when T equal to T0, the theta would be, when this equal to T0, that would be T0 minus T0 divided by Q1 R over K. Okay, so that would be equal to 0. Okay, and then when for example T, when is the theta equal to 1, that would be when T minus T0 would be equal to Q1 R over K. Okay, so this condition would be held. Okay, so that would be this one, and then the last one is the zeta. Okay, so zeta is the dimensionless number for distance for z. It is quite more complicated, so we have to put the zk divided by rho cp v z max r square at this one. But if you want to try to put all the units, that would be also the dimensionless number. Okay, so here we can see that that would be the dimensionless form of the equation. So if we substitute this equation, okay, this one, so we substitute both of them. For example, what is dou t, what is dou z, and then we substitute them, that become this one. Okay, so this will become this one, this equation. Okay, so and then this equation will have a boundary condition when c equal to 0, or when r equal to 0, which is the theta is finite. Okay, the temperature is finite, or if we change with the dimensionless number, would be t is finite. Okay, in here the boundary condition 2, when r equal to capital R, then the sorry, this one, yeah, in the capital R, we know that the delta would be 0, or there would be a Q1, and then change the Q1, there would be a Q1, and then here we change it into this one, okay, from that one there. And then the last one, when this one, when z equal to 0, theta equal to 0, we change it into dimensionless number, that will become tau would be equal to 0. Okay, so that would be the boundary condition for that one. Okay, boundary condition is or the dimensionless number is sometimes very important for us if you have a very complex equation to start with. Okay, so another one for some cases, a special case for if you have a very high zeta, the temperature fluid will be linear with z, so that would it is not similar with the boundary condition 3. So the boundary condition 3 would be like this. Okay. Okay, so and then we can substitute up to here to do integration. So this is just another special case, and then you will get again the distribution of temperature if you have a higher data, but it would be not included. Okay, that one there, and it would be a function of Reynolds and Prandtl. Later on, just some additional calculations. Okay. All right, so that is I think our exam for the energy transfer would be up to here, up to the you should be able to also convert the the equation into the dimensionless equation. Okay, and then the last one, let's just think about this one, free convection. Okay, so in free convection, let's just consider that we have fluid. Okay, so we have a fluid, and the fluid is between two parallel plates, okay, with difference of temperature. So we have two plates over here, this side and this side, and this temperature has this plate has different of temperature. For example, this is the temperature profile. Okay, so this is the temperature profile, and after that, because of the temperature profile, then the property will also change. Function of T. Okay, so the with the properties would be a function of T. So because of that, so for example, let's see again the distribution of temperature first here. So let's see the distribution of the temperature. This is the volume element, and also K is the constant. So this is the we check. You can try this from the try to use the energy balance, and then you add the Fourier equation, and then you get this equation, okay, between conduction between two parallel plates. Okay, so here, and then with some boundary condition, when uy equal to minus b, T has some temperature, and y equal to plus b, T also has some temperature. Okay, so here you have temperature difference, the distribution of the temperature, which is between those parallel plates. I know that maybe I can delete that one. Okay, so I think okay, so maybe between, if you have a two parallel plate like that, and then you want to know the temperature, if this is, for let's say this is T2 and then this is T1, so the delta T would be with the reference would be T1 over T2, or maybe like this. Okay, so this again the temperature profile. Or maybe you know this a lot in conduction, I guess, in the OPK ya, peristiwa operasi perpindahan kalor, but it's actually this is just the how we find the formula from the derivation of the formula. Okay, and then here with the momentum, okay, if we have the also momentum balance with the similar volume element, we will also find that between two parallel plates, that would be mu dvz d square vz divided by dy square equal to dp over dz plus rho g. You can try it again. So the function. So so that means that you have temperature profile, you have velocity. You have also momentum profile. Okay, that one, because of the difference of that one. Okay, now because of you have a temperature profile, then it will affecting the rho. Okay, it will be affecting the rho. Why? Because the rho is actually a function of temperature. Okay, so rho is actually a function of temperature, and then if we consider that mu is constant, rho is a function of temperature, and then we can expand it with a Taylor expansion. You know, the Taylor expansion is like this one, so rho at t plus the difference of rho, yeah, this one, rho to the t multiplied with delta t plus dou rho over dou t at this is actually square the second derivation, t minus t square plus blah 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 blah. Yeah, this is Taylor expansion, but we don't need that one. We need just some one coefficients. Okay, so it's basically, we can say that we make rho, or the density, is a function of temperature, and then this is the function, which is rho minus rho beta t minus t dash. Okay, t dash is some reference temperature, but we haven't defined this one. Okay, so long story short, then we actually can change, so we can substitute equation of momentum transport with rho, yeah, and then this is function of temperature. So we basically substitute the equation for momentum balance in this those element. It's a function of rho, but for the density we can't say that it is a constant density because we know that there is a temperature difference, temperature distribution. Okay, so what happened is now if we substitute, we look like this one, and this one is called the buoyancy forces or gaya viscous. Okay, so that means that this is actually a viscous force, and this is called buoyancy forces. So the forces, or this is because of the difference of temperature, so they will have some difference in density, and that difference of density will have a force, ya, jadi gaya buoyancy. Okay, so this is viscous force. Then this one is buoyancy force. Okay, and because of that, because of this viscous force, and then also because of the buoyancy force, then that would be a free convection. Okay, there would be a temperature difference because of viscous force and also the buoyancy force. Okay, so and after that we can, so if we want, we can get the distribution, the temperature distribution over here. So it is here, yeah. So the T we change it with the temperature distribution, which is this one. Okay, and then with some boundary condition, and then added some dimensionless number again. So this is dimensionless number, which is, this is called mu. Yeah, mu would be a dimensionless number for the distance, for the thickness, yeah, perbedaan thickness, and A is for the delta T with some graph number. And then after that we will find the physi. So the physi would be the velocity caused by those buoyancy forces. Okay, and if we consider this as a dimensionless number, then theta would be like this one. So at least, the long story short, we find that there is a Grashof number. Okay, so that's why in free convection, I said that it would be a function of Grashof number and Prandtl number, and this is the Grashof number, which is a function of the delta T, and also those beta on the top, and also the rho. Okay, so here is actually, so for in the free convection you need to consider Grashof number to get the temperature difference, and also what is the velocity that is caused by the difference of the density. Okay, it looks like in the concept looks like simple, yeah, because of the you have something hot. For example, I have this let's say I have this candle, and then it is heated up, and then the candle heated up the flame, okay, and then it's heated up some of the air outside on the top of this one here, and then there would be a movement of the air. Okay, and then the movement of the air is caused temperature difference. That is the concept of free convection. But when we look at the formula, it becomes very complex. Of course, it's not gonna be put it in the exam, of course, but at least you need to know the concept of free convection, and then how it's gonna use. So it's gonna use this Grashof number, and also the principle of the free convection. Okay, so I think that would be conclude. So this would be the forced convection and free convection as has been explained. Let's have a quiz, yeah, on Friday, and the quiz that I will give is actually the momentum back again, a momentum transfer with shell momentum balance, and also momentum transfer with equation, okay, with equation of change. Okay, it's basically maybe to heat it up for the next week's exam. All right, everyone. I think that's all for today. So thank you for listening. And in some time, I will give maybe like a Google form to just to check which one of you who can attend and also who can't attend because of maybe health reason. And then just wait for the next information from me. Okay, so this is a plan A, but the plan B, if the case is increasing again and so on, and then of course we have to maybe need to cancel it. Okay, all right. Okay, thank you very much for your attention, and then I'll see you again on Friday. Bye bye.
Thank you, Bu.
Yeah,
Thank you, Bu.
okay.